Whoa, this one's a doozy, huh? A multiverse outside the swampland. You weren't kidding when you said you found a dense one.
Yeah, not exactly light reading.
But hey, diving into this kind of stuff is what we live for, right?
Absolutely, and this paper is really interesting.
So before we get too far, let's lay it out there. We're talking about the multiverse.
Right, right.
But specifically, this paper dives into whether a multiverse can exist without completely changing the laws of physics as we know them.
Yeah, and that's a really important distinction to make right up front.
Absolutely. And to help unpack it all, we've got expert speaker here who I'm pretty sure can explain even the most brain-bending concepts in a way that even I can understand, right?
Well, I try.
So let's start with the big question. Can we even have a multiverse? You know, this idea of countless universes beyond our own and still make it work with, well, with the physics we know.
Well, and that's what makes this paper so fascinating. Because they're essentially trying to impose rules on something as infinite as the multiverse. So instead of just this free-for-all of anything is possible, they're saying, hold on, there might be some actual guidelines, some cosmic rules, if you will.
So you can have a multiverse, but you got to play by the rules.
Precisely. And those rules, in this case, are what physicists are calling the Swampland, which is kind of a scary term, but it's basically this region where theories, however cool they sound, kind of fall apart when you try to mesh them with like a unified theory of everything.
So there's a cosmic bouncer, right?
Yeah.
Exactly. Is the multiverse going to get past the velvet rope or what?
Yeah. Exactly. It's about, can this concept of a multiverse, with all its crazy implications, can it actually fit within the framework of everything else we know about physics?
I like it. Now, for those who maybe skipped a few physics lectures, how would you even explain this whole multiverse concept to someone who's like, wait, there might be more than one universe?
Right. Well, the easiest way I can think of explain it is, imagine our universe, vast as it is, right?
Hmm.
All the stars and galaxies, it's just one bubble in an infinitely larger cosmic foam.
Well,
And in that foam, each bubble is its own universe, potentially with its own set of physical laws, its own history, its own, maybe even you and me, but slightly different.
okay, see, now my brain hurts. But before we get too far down the rabbit hole, this paper actually lays down two fundamental rules, right?
Right.
The distance conjecture and the refined de Sitter conjecture.
Mm.
And now we don't have to get into the really nitty-gritty math here.
No, definitely not.
But what's the general idea behind these conjectures, and why should we even care about them?
Okay, so think of these like the ground rules for building a universe. So like the distance conjecture basically says you can't just cram unlimited amounts of energy into a tiny space.
There are rules.
There are rules, exactly. So beyond a certain limit, things get wonky, right? It's like the universe's circuit breaker.
So no stuffing a universe's worth of energy into a bread box.
Basically, yeah.
I got it.
Yeah.
Okay, what about this de Sitter conjecture? What's that one about?
Okay, so that one's a bit more abstract, but essentially it deals with like the shape of the universe's energy landscape. So picture hills and valleys representing different energy levels, right? The refined de Sitter conjecture essentially says those hills and valleys can't be too steep and they can't be too shallow if we want our universe to actually, behave the way it does.
So these conjectures are kind of like, they're guidelines for the universe. Like they're
Yeah.
saying, hey, if you want to exist, here's what you got to work with.
They're signposts, guiding us through this maze of all these theoretical possibilities.
Okay, so we've got a multiverse, we've got cosmic guidelines, and we've got a research paper that's not afraid to get a little weird. This is where things get really interesting. All right, we're back. So far, we've got cosmic guidelines, a new spin on eternal inflation, and a pretty big head-scratcher when it comes to our own universe's observations. But now, we're about to climb Mount Improbable itself, uphill universe creation. Is my coffee strong enough for this, or are we about to break reality?
Fasten your seatbelts because it's about to get even weirder. So far, we've focused on how this model churns out universes, each with its own unique set of properties. But to get to a universe like ours, with its specific laws and constants, we need to talk about quantum tunneling.
Okay, quantum tunneling. I remember that term always sounded like a magic trick physicists use to get out of tough explanations.
It does sound a bit like that, doesn't it? But it's actually a real phenomenon in the quantum world. Imagine trying to get past a wall instead of going over it, you punch a hole straight through. That's essentially what quantum tunneling allows particles to do at the subatomic level. They can bypass energy barriers that would normally be impossible to overcome.
So if our universe is one big cosmic construction site, quantum tunneling is how we sneak in materials past the building inspector.
That's a fantastic way to put it. And in this paper, quantum tunneling is how they propose new universes might pop up, within this eternally inflating space.
Okay, I'm with you so far. We're picturing baby universes tunneling into existence. But here's where I need your help. The paper mentions tunneling to states with higher energy. How does that work? Isn't everything always trying to settle into a lower energy state? Like rolling downhill, not up?
You've hit on the most mind-bending part of this research. Usually we picture tunneling as a shortcut down an energy hill, moving from high energy to low energy. But this paper argues that under very specific conditions, tunneling can actually happen uphill.
Whoa, uphill tunneling. That's like watching a river flow up a mountain. How is that even possible?
That's where we get into some seriously heavy physics, involving something called a Hawking-Moss instanton.
Oh no, not the instantons. Anything but the instantons.
Don't worry, I'll spare you the technical jargon. Think of it like this. Imagine those energy hills have secret passages, hidden tunnels that allow for these uphill jumps. It's like finding a cosmic back door to a higher energy state.
Okay, so uphill tunneling check. What happens once a baby universe tunnels its way to a higher energy level? Is it smooth sailing from there?
Not quite. The paper describes a dramatic birth from something called a false vacuum. Imagine a tiny bubble rapidly expanding within this higher energy state. From outside, it looks like it's growing larger, but from inside that bubble...
It's a whole different story.
Exactly. From inside, the universe appears to be shrinking rapidly. The walls of this bubble are closing in. But then, just as it seems like it's all going to collapse, the throat connecting the bubble to its parent universe pinches off.
And boom, a new universe is born.
Precisely. A dramatic process fueled by quantum fluctuations and governed by this complex dance between gravity and energy.
This is incredible.
Yeah.
But I keep thinking back to that little problem we have, the mismatch between this model's predictions and the cosmic microwave background radiation, that afterglow of the Big Bang.
Yeah.
Does this uphill tunneling explain why our universe looks the way it does? Does it solve that piece of the puzzle?
That's the million-dollar question, and as it stands, this model still needs some work before it can fully explain our universe. The researchers acknowledge this. They've given us a fascinating framework, a new way of thinking about a plausible multiverse, but they haven't quite figured out how to connect all the dots to our reality just yet.
So the mystery continues. But I've got to say, even with these unanswered questions, I'm completely captivated by the ideas in this paper. We've gone from quantum nudges to universe birthing bubbles and uphill energy climbs, and I feel like we've just scratched the surface of this incredible cosmic landscape.
That's the beauty of theoretical physics, isn't it? It's like exploring a vast, uncharted territory with new wonders and mysteries waiting to be discovered around every corner. Every answer we uncover seems to lead to even more profound questions.
That's a perfect note to end on. Thank you for being our guide on this mind-bending journey. And to you, our intrepid listener, until next time, keep looking up, keep asking the big questions, and never stop exploring the universe within and the infinite possibilities beyond. All right, so we're back and ready to tackle this whole eternal inflation thing. We talked about it a bit before, but this is where the paper gets really interesting. Because they're proposing a version of eternal inflation that actually, well, it kind of tries to behave itself.
Right, because the traditional model, it can get a little, well, messy, right?
Yeah, like how messy are we talking?
Well, it often requires these really extreme conditions, like those super steep energy landscapes we mentioned earlier, and that can actually create problems.
Problems like landing us in the swampland, breaking those cosmic rules.
Exactly. It's like trying to build a house on a foundation of jelly. It's just not going to hold up.
So is eternal inflation just a bust? Is this where our multiverse dreams go to die?
Not so fast. This is where the paper takes a really fascinating turn. See, instead of ditching eternal inflation completely, they propose this kind of new and improved version, something they call the hilltop potential.
Hilltop potential.
Yeah.
Okay, back to our energy landscape. I'm picturing something, but I'm going to need your expert guidance on this one.
All right, so picture this. You've got a ball balanced precariously on top of this hill, right? Even the tiniest little nudge can send it rolling down one side or the other.
Okay, got it. Precarious ball on a hill.
Now, in this model, instead of just a smooth roll down one side, imagine the universe is constantly being jostled by these tiny quantum fluctuations right there at the hilltop.
Okay, so instead of one big push, we've got this kind of constant, almost chaotic energy landscape.
Right, and those random little quantum nudges, every now and then, they're going to push the universe over the edge, and when that happens, boom, you get this burst of rapid expansion inflation, and a new universe is born.
So every nudge is like potentially a whole new reality. That's a lot of pressure for some tiny fluctuations.
Yeah, it's kind of mind-blowing when you think about it, right? But here's the thing. The researchers show that this kind of eternal inflation, this hilltop version, it can actually occur under surprisingly mild conditions. So we don't need those crazy steep energy hills. We don't need energy levels that are off the charts. It's like finding a way to have your cosmic cake and eat it too.
Okay, this is all sounding a little too good to be true. There's got to be a catch, right?
Well, there might be a slight hiccup. While this model seems to solve the whole eternal inflation problem, it runs into a bit of a snag when we try to reconcile it with what we see in our own universe, specifically the cosmic microwave background radiation.
The CMB, right? The afterglow of the Big Bang, the oldest light in the universe.
Exactly. Now, this hilltop model, on its own, it predicts a pattern of fluctuations in the CMB that doesn't quite line up with our observations. Basically, the predicted fluctuations are too large.
So close, but no cigar. Does this mean the whole hilltop idea goes out the window, or is there a way to salvage it?
Well, it might not be game over just yet. See, the researchers, they suggest this model could be one piece of a much larger, more complex puzzle. So maybe, just maybe, this modified eternal inflation, it's responsible for the initial spark, the birth of universes. But then there's something else, some other mechanism that kicks in and shapes those baby universes into what we observe today.
Okay, so I've got a potential starting point, but the story of our universe might be a bit more complicated than just eternal inflation.
Exactly. And that's where things get even weirder. Because to understand how those universes actually take shape, we have to dive into a concept that's even more mind-boggling.
Oh no, more mind-boggling than a multiverse generated by quantum foam. What could possibly be weirder than that?
How about universes being born uphill?
Uphill? Wait, isn't everything always trying to, roll downhill? Move towards lower energy
I
states?
think so, right? I mean, that's kind of how we understand the universe to work, generally. But this paper, it throws us a real curveball. It suggests that under some very specific conditions, tunneling, that quantum tunneling we talked about earlier, it could actually happen uphill.
Wait, uphill tunneling? Like watching a river flow up a mountain. How does that even make sense?
That is the million-dollar question, and this is where we get into some seriously complex physics, involving something called a Hawking-Moss instanton.
The instantons.
Yeah.
Anything but the instantons.
Don't worry, I'll spare you the technical details. Think of it like this. Imagine those energy hills we were talking about. They've got these secret passages, these hidden tunnels that actually allow for these uphill jumps.
Okay, so uphill tunneling. Check. Now, what happens once a baby universe tunnels its way to this higher energy level? Is it smooth sailing from there?
Not exactly. The paper describes this incredibly dramatic process where the baby universe is born from something called a false vacuum.
A false vacuum. Okay, I'm already intrigued.
So picture a tiny little bubble, right? And it's rapidly expanding within this higher energy state. Now, from the outside, it looks like it's growing bigger and bigger. But here's the thing. From inside that bubble,
Okay, from inside the bubble, it's a whole different story.
exactly. From inside, the universe appears to be shrinking rapidly. The walls of the bubble are closing in. And just when it seems like it's all going to collapse, the throat, that connection point between the bubble and the parent universe, it pinches off.
And boom, just like that, a new universe is born.
Precisely. This incredible, traumatic process, all fueled by these quantum fluctuations and governed by this complex dance between gravity and energy.
This is mind-blowing stuff.
Oh,
But I keep thinking back to that little problem we had earlier. The mismatch between the model's predictions and the cosmic microwave background radiation.
yeah.
Does this uphill tunneling, does it explain that? Does it finally solve that piece of the puzzle?
That's the thing, isn't it? As it stands, this model, it still needs a bit more work before it can fully explain everything we observe in our universe. And the researchers, they readily acknowledge that. They've given us this incredible framework, this really new way of thinking about how a multiverse might be possible, but connecting all the dots to our reality, well, that's still a work in progress.
So the mystery continues. But I gotta say, even with all these unanswered questions, the ideas presented in this paper, they're absolutely captivating. I mean, we've gone from quantum nudges to universe birthing bubbles to uphill energy climbs, and I feel like we've only just scratched the surface.
That's the beauty of theoretical physics. It's like exploring a vast, uncharted territory. There's always something new and incredible waiting to be discovered just around the corner. And sometimes those discoveries lead to even bigger, more mind-blowing questions.
And that is a perfect place to wrap up our deep dive into the multiverse. Thank you for joining us on this wild ride. And remember, keep looking up, keep asking those big questions, because who knows what incredible wonders are waiting to be uncovered.